All right, in today's lesson we're going to look at two different models of EMR and how they travel. In any topic, scientists always try to come up with new ideas, they prove them, they refine existing ideas, they try to make things better, try to disprove a different theory, and so on. And EMR and light in particular is a topic that underwent lots of battling back and forth, and proving and disproving, and so on. And it sort of divided the scientific community. So what we're going to do is kind of go back in time to look to see at how scientists thought of light worked and how it changed and then what it's like today. So there's basically two different groups. We're going to look at the particle model, so thinking that light is sort of like a little particle, just like a ball that you would throw, and it travels along to pass the energy. And then the second one we're going to look at is light travels as a wave. So just like we looked at waves in Physics 20, we're going to think that one of that way. So is it a particle or is it a wave is sort of what we're looking at today. We're going to start sort of with our master of physics, and that's our good old buddy Isaac Newton. And he's the one that first proposed the particle model. And because it was Newton, and because he was right about a lot of things, the science world sort of backed him up and agreed. And Newton had some pretty solid theories and proof of why it was a particle. He said light travels in a straight line. So when you throw a ball, it travels in a straight line, unless there's some other force act on it, like gravity or whatever. And if we shine a flashlight on somebody, it creates a shadow. So obviously the light's going in a straight line, and the person or whatever the object is blocks out those beams of light. So therefore, you think of them as little particles. They would hit an obstacle like a person, and that doesn't pass through, so that's why we get the shadows. And he also said particles can be reflected. So if you throw a ball and it bounces off the wall, it comes back at you. Light does the same thing. If we shoot light off a mirror, it bounces back. And probably his biggest proof of why it was a particle is we knew that waves had to have a medium. A wave had to travel through something. It has to travel through water to get water waves. It has to travel in a rope to make a wave on a skipping rope, and so on. And he said light coming from the sun has to be then a particle, because how would it travel through space? If there was no medium, space is just basically a vacuum. Therefore, it has to be a particle that could just travel through that empty void. Later on, some scientists started to say that, well, maybe Newton's not quite right. And the first was Christian Huygens. And what he looked at was sort of Newton's idea that light has to travel in a straight line. That's why we get shadows and things like that. He started looking at a shadow around an object, and he saw that the edges were sort of blurry. So he was like wondering why would they be blurry? If light was traveling in a straight line, it would be kind of like, imagine if you make a stencil and you spray paint the stencil. So if I had a cutout of letter A and I spray paint around it, right, all the paint would go outside the A, and then where the A letter would be, that would block the paint. And if we lifted it off the paper, we'd have a perfect A mark from where the paint didn't touch. So he was saying if it was particles, that's what it would look like. But if we actually look at a shadow, the edges are kind of blurry and kind of fuzzy. So what he did was he started looking at better quality shadows. So what they did was they would use a high intense light and shine it on a disc to see what kind of shadows were created, and to try to see if there's any kind of patterns. So if this kind of diffraction patterns go on, their logic is that light is actually bending around the shadow a little bit, and we're getting sort of interference when it goes around. So Huygens actually proved this to be true. So this little picture I have at the very bottom, this is a shadow pattern that's created with a high intense light around a solid disk. And because the waves are interfering and we get constructive and destructive interference, we get these kind of weird little patterns going on. And earlier there was a French scientist named Simon Poisson, and he predicted that light had to be a particle because there's no way we'd get shadows around the disk. And he said, well, if they actually did, we'd end up getting a dot in the middle where they would be constructive interference, and that never happened, so it has to be a particle. And Huygens and guys that believed in the wave model actually proved that the Poisson was totally wrong. And a guy named Dominic Arago actually later on produced what Poisson was saying that never happened. He actually did it with a pretty intense high-powered light, and we got the picture that we see at the bottom. So they kind of named it the Poisson spot to say, well, because he was such an idiot and was totally wrong, they kind of named it that as a joke. So there were still some people that were saying Huygens wasn't right, and part of it where they were sort of saying, well, how does it work when when light hits water? We get glare, reflection off the water, but some of the light actually passes through. So what Huygens actually did, he said, well, it has to be a wave, and he measured this in an experiment. So he said if we had an incident wave of, let's suppose it was an amplitude of 5, he then measured how much of the wave got reflected. So let's suppose 2 of it got reflected, and then he measured what went through. It was transmitted into water, and it was 3. So what he found out was that original 5 broke up into 2 equal parts that added up to the original. And he said it acted just like when we have wave interference. So if you remember in Physics 20, if we had a wave of 3 and another wave of 2 approaching each other, they would join for a wave of 5 and then break back up into the 3 and 2. So he was saying it did the exact same thing when he did this with light, so therefore it had to be a wave. They then approached Newton to sort of explain how did that work, and Newton came up with a pretty lame explanation. He said that the particles that are coming in hit the water. Because they're smashing into the water, they get all excited and have a fit or get all bouncing around. Some of them decided to jump off and get reflected. Other ones decided to go through. And pretty much at that point, since it was just such a pathetic response, Newton lost any support for his particle model. So then it was quite a few years later that people sort of started following the wave model. So with Huygens' ideas, along came a guy named Thomas Young, and he did a double slit experiment, which we're going to look at later on. But basically, if you have a small microscopic slits, you just cut these with like razor blades, really tiny slits, and we shine light through it. So we have some sunlight or whatever shining through. We actually get interference patterns, just like you would with water waves on the other side. So because of that, we get these highs and lows and bright spots and so on. Thomas Young said, well, it has to be a wave if we're getting wave interference. And from then on, pretty much for about 100 years, everybody accepted the wave model. What happened, though, later on, and this is like late 1800s, early 1900s now, other scientists came on and said, well, hold on a second, maybe Newton might have been right or might have been onto something. And the first was Max Planck. We're going to talk about him later, but he sort of came up with what he called black body radiation, and he said that the light and the energy, the EMR that was being absorbed, went in levels. So that meant sort of like particles or bundles, so nothing happened until we hit a certain level, till you had enough light, and then the energy would jump. So he called them quanta, which just basically is a Latin word for bundles. And then Einstein went one step further and attached that to the light theories, and he said then light actually travels as little particles or little quantas, which he called photons. So we got a little bit of a problem. Huygens and Young and these guys proved that light had to be a wave. Planck and Einstein are now saying that light has to be a particle, which basically leads to our modern theory. So because there were sort of these two different ideas, we now see that depending on the situation, some are right. So we're going to look for this chapter that we're on now. We're going to basically treat light as waves, and we're going to do wave theories, and everything that we do with waves is to show that that's true. Then, when we get to the next chapter, we're going to look at more of Einstein's and Planck's sort of ideas, and we're going to look at light being particles. So today's current way of doing it is we say light is actually a particle that travels in a wave pattern, is typically how we think of it now. And that's all.